I don't think I'll ever.
Okay, let's go ahead and get started.
Probably not.
As you know, we have an exam coming up on Friday. It opens on Friday and stays open through Monday. Please remember that on Monday, the testing center closes early, so don't get caught outside the door. On Tuesday of next week, we'll go over that first exam in all its gory detail, and then on Wednesday, you'll get a do-over with the exam B. I posted 2 exams and their solutions at the MAT site, so you might want to think of going and working one of those exams or both of those exams. Today we're gonna rely on some of your experience outdoors. Many of you have been hiking and you've used a topographical map, and in these maps, each one of these squiggly lines represents a certain elevation above sea level. And on several occasions, I've compared voltage to elevation, that voltage plays much the same role in the electrical problem as elevation plays in the gravitational problem. Now, just looking at this map, you can see where we've got a gentle slope where there's a big horizontal distance between 2 lines of elevation. If each of these were, 10 meters apart, then I could go quite a ways before I had to climb 10 meters. On the other hand, over here where they're close together, that would be a very steep slope where the lines are bunched up. And then this might be a place where you don't want to hike in the dark because you'll fall off a cliff, or this ridge right here. And what we're going to find is that we can do this same thing with voltage. We can draw lines where the voltage is all the same, and that will give us a visual of what the electric field looks like in the region. Okay. Last day, we discovered what I call the Ed equation after Mr. Ed, the talking horse. Wow. And it's just so brutally simple. You know, if you want the voltage between one point A and another point B, it's just the electric field between those points. That's the E, and the distance between those points. That's the D. And yet, with all its simplicity, I find it's the equation that gets people into trouble the most. Okay, and I'll show you why. First of all, you can only use that equation when the electric field is uniform, everywhere the same, everywhere the same. And we know that is true between charged plates or near a single plate if you're very close to the plate. But those are the only times when you can use the Ed equation. Don't be dragging it out for everything. If I want to know what the electric field is between these plates, and let's say they're big compared to the 1 centimeter between them, I hook them to a 12-volt battery, and there's going to be a voltage difference of 12 volts from the negative plate to the positive plate. As you found in tutorial this week, that's the battery's job. That's what it does. It keeps the voltage 12 volts between those 2 plates. Now, if I use the Ed equation, I have to define the voltages between some point A and some point B. Well, I know the voltage between the negative plate on the left and the positive plate on the right is 12 volts. And so I can put that into my Ed equation. Now, here's where people run into trouble most of the time. If I've got the voltage difference between that point A and that point B, I need to have the distance between that point A and that point B. If I want the voltage between A and some other point, say the middle of the plates, I've got to use that distance. I have to use that distance. These indices right here have to match those indices there. And that's why I encourage you to use those indices just to make sure that you're not making a mistake during the exam. Okay? Now, in this case, I just asked you what's the electric field between the plates. That's not what I'm going to ask on the exam. No, because Greg is evil. Greg is going to ask you, what's the electric field 1 millimeter from the positive plate or 2 millimeters from the negative plate? Is that important? No, the electric field is everywhere the same between those plates. It doesn't matter where you look between those plates, it's exactly the same. The field lines are parallel to each other. And that's what tells me it's uniform. Okay? And so don't get tripped up by that. Now, if I take, make sure that distance from A to B is what you're using. So if I solve for the electric field by dividing both sides by the distance, which is 1 centimeter, I get 12 divided by, I've got to put that in meters. I can't put that in centimeters. And what I get is 1200 volts per meter. Now it's really, really easy, trivial indeed, to show that volts per meter is exactly the same as newtons for each coulomb. And so those are equivalent. We can talk about the electric field in volts per meter, or we can talk about the electric field in newtons for each coulomb. When you're using Coulomb's law, it's better, it's easier, more intuitive to use newtons for each coulomb. But when you're looking at this topographical map and you want to figure out where the electric field is big, you want to use volts per meter. How big is the change in voltage for 1 meter of distance? Okay. Now I'm going to show you 3 slides that you've seen before, and you're going to see them again on Thursday. These are the slides that everything hangs on. The 3 slides to rule them all. Okay. The first one is just the definition of voltage. And by voltage, I mean voltage difference between A and B. It's got 2 definitions, really. If I take 1 coulomb plus 1 coulomb from A to B, how much do I fill up that electric potential energy bucket? Okay. And if I know how much I'm filling it up for 1 coulomb, I can figure out how much I'm filling it up for 2 coulombs or 3 coulombs or 5 coulombs just by scaling it, just by multiplying by whatever I really bring from A to B. Now, the second way to think of it that is more intuitive, something I can actually wrap my brain around, is if I take that 1 coulomb and I start from rest and I push slowly to point B and stop, because I started from rest and I ended at rest, I didn't put any energy into the kinetic energy bucket. All of my Verk, force times distance, went into filling up that electric potential energy bucket. And so all I had to do is figure out how much Verk I had to do to take it from A to B. Now, in practice, when we're dealing with protons and electrons, we don't do any external Verk. Okay? That idea of just grabbing 1 coulomb and pushing it from A to B, that's just to give me a mental picture of how much electric potential energy I'm storing. Okay, but in practice, I just take that proton and let it go. Okay, it's like kicking the boulder at the top of the cliff. Let it go. In those cases, the Verk done by me, the external agent, is 0. Absolute nothing. And that means that I've got to have a zero-sum game. Any increase in kinetic energy at the bottom of the cliff has to come from a decrease in potential energy. Okay? As it goes from a high elevation to a low elevation, or in this case, from a high electric potential energy to a low electric potential energy. When one bucket fills, the other bucket drains. And that idea is the starting point for every single voltage problem that you'll have on the exam. The other thing I want you to see, and we've seen it before, is that the voltage difference from A to B is a rate, just like the electric field is a rate, like the price of a gallon of gas. And so the electric force depends on the electric field in the same way that the electric potential energy, the change in it, depends on the change in voltage. We figure out what they mean by setting the test charge equal to +1 coulomb. And if the test charge is +1 coulomb, then the force is the electric field. The electric field is the force that 1 coulomb would feel. Okay, play it backwards. Likewise, the electric voltage from A to B is the change in stored energy, electric potential energy, by taking 1 coulomb from A to B. That's the way you visualize what these things mean. See if your neighbor can see that, if that speaks to their soul.
No, we do. Oh yeah, because
I think this last one is like,
Okay. I've said on a number of occasions that there is only one voltage problem, and here it is. It was in your homework. Homework 10, problem 3. A proton has a velocity of 1 × 10⁵ meters per second at point A, and then when it gets to point B, it's going faster at 3 × 10⁵ meters per second. If I'm told that the voltage at point A is 1,000 volts, what is the voltage at point B? Now, so that we can all visualize what's going on here. So here's what we have. When we see this proton at point A, it's going at 1 × 10⁵ meters per second. And the voltage at A is 1,000 volts. Now, I'm sure you have noticed that velocity starts with V and voltage starts with V. And that's not my fault, okay? That just is. That's the English language. And so to try to make sure that we don't get confused by those ideas, I'm always going to write the voltage as a blocky V, as blocky as I can make it. And I'm going to just always make the velocity V just French and curly, okay? Just as squiggly as possible so that we can make sure that we understand which is which. Okay, now, first of all, put on your crap detector. Are you expecting an answer for the voltage at B to be bigger than 1,000 volts or smaller than 1,000 volts? Tell your neighbor, bigger than 1,000 volts or smaller than 1,000 volts?
Because the lot
Okay. You remember that protons are positive, and so they speed up in the direction of the electric field. And the electric field is from high voltage to low voltage. They speed up downhill is one way of thinking of it, okay? And so I'm going to need a voltage at the end of my calculations. I better get a voltage that's less than 1,000. That's less than 1,000. So let's go and look to see what we get. Now you had different numbers in your homework. Everyone had different homework problems, but this is basically the problem that you have. So we start from the grand high Verk energy equation, and that is just that the external Verk changes the energy. And I've got two buckets: the kinetic energy bucket, how fast it's going, and the electric potential energy, where it is on that cliff. Okay. Now, because we never touched the proton, because I don't even know how I would. Okay. It's just flying through space. That means that this Verk has to be zero. Okay. Zero. And that's the case 99.9% of the time. And if that's zero, that means that these have to trade off of each other. If this one is +6, that's got to be -6, right? Because it's got to add up to zero. And so this is the starting place for most of your problems. Nearly all of your problems start right there. Okay? The change in the kinetic energy bucket is exactly the same as the change in the electric potential energy bucket, but with a minus sign. And that minus sign says that if one of them's filling, the other one's draining. When you see that equation, what you should be seeing is that, okay? If this is +6, that's got to be -6. It's draining. Now, the kinetic energy bucket, we can define the change in kinetic energy just as final minus initial. We can do the same thing with the voltage, the electric potential energy bucket, but we usually don't. In this particular problem, you're told what the voltage is at point A. It was arbitrarily given as 1,000 volts. But in general, you don't really care. You just care, what's the change in voltage? What's a change in voltage? Okay. Now, that's where we start, and that's the end of the physics. After that, it just becomes memorization. This is what I mean by change in kinetic energy. This is final. Its final point was B. This is initial. Its initial point was A. And then I've got to have this minus sign. And folks, the voltage problems are where the minus signs are everything. Okay, you've got some homework problems where there's 3 different minus signs, each meaning something different. Okay, and you have to keep track of each and every one of them. Okay. Now, if I plug in for everything, again, this is just memorization. Kinetic energy is 1/2 mv squared, 1/2 mv squared, and that's going to be on the front page of the exam, just like the equation sheet that I gave you. Okay. And then I plug in my values. Okay. I know that that's 1.6 times 10 to the minus 27. I know that that is 3 times 10 to the 5th. I know that that's 1.6 times 10 to the negative 27. That's 1 times 10 to the 5th. That's 1.6 times 10 to the minus 19. I know everything except for delta V from A to B. And so I just solve it. You see that this over here is positive. The left-hand side is positive. That means the right-hand side is positive. Since this is negative, I've got to have a negative change in voltage. And indeed, when I solve for that, I get a negative 417 volts. Now, folks, we got 2 groups in the room right now. We got one group that looks at that equation right there and just says, oh, that's just algebra. I can do algebra. For those people, this next exam is going to be the easiest exam of the semester. Okay. There's another group in here that are looking at that and freaking out. What? That's messy. This is going to be the hardest, most difficult exam of the semester for you. I'm just saying. Okay. That's how it's going to play out. Now, if my initial voltage was 1,000 and my change is negative 417, now we're just balancing the checkbook. Okay. That means the final voltage has to be 583 volts. Check on your neighbor, see if your neighbor is still breathing.
Yeah, I won't remember it what. It's nice. I need to figure it out now.
Go to the basketball game tonight.
I also, the masses even canceled.
Okay,
I mean, it's fine.
Yeah.
are there questions?
Now.
Any questions?
I hear you, actually, right.
Okay. That's too bad, because I was wanting to check out my new microphone that I just got here.
I got one for you.
Okay, let me start the
Microphone,
transcription.
Okay.
I've got this transcription program and I tried it out at the restaurant with my wife's siblings last night, and it worked great. It just worked wonderful. But then I realized that I had used up an hour and a half and they only give me 5 hours a month. So I'm just going to turn it on right when I have a question.
So, in the previous problems in last semester, we did these really mathy problems. We use sine and cosine. Is sine and cosine ever going to come into play with voltage?
No. The question was, are we going to have sine and cosine in here? And that, no, because we're dealing with energy, and energy, remember, is a scalar, doesn't depend on direction. And so the only time that sine and cosine would come in is if you're doing Verk by pushing at some angle relative to the direction of motion. And because most 99.9% of these problems, there is no external Verk, those sines and cosines go away. Okay. Well, I'm really pleased with that. Okay. 1999, and I bought one for $200, and it doesn't work worth a darn. I'm gonna have to send that one back. I've got another question in the back. Let me start up this again.
The last line in the text when the negative Q test, do we know what that is, or do you set it to?
Oh. This minus sign doesn't mean it's a negative test charge. This minus sign comes from this equation here that says that if that's +6, that's got to be -6. So that minus sign always goes there and we carry it down. Now, if this were an electron, I would put in a -1.6 times 10 to the -19 coulombs. But because this is a proton, I'm putting +1.6 times 10 to the -19 coulombs. Okay, so this minus sign is just a part of whatever goes up must come down. Okay. Sweet, it got all of that. When I was alive, we didn't have this technology. It's just amazing. Back then, I would have been just totally out of luck.
Yeah.
Okay. If I were to ask you, are any of these points, A, B, C, or D, at the same voltage as the X? Tell your neighbor, are any of those points, A, B, C, or D, at the same voltage as the X? Okay. So I hope you all said that B and D are at the same voltage as the X. Now, there's several ways to think about this. One, remember I said we got higher voltage near the positive plate and lower voltage near the negative plate. And that means that point A is going to have higher voltage than point C. And indeed, point A is going to have higher voltage than points B and D. And B and D are going to have higher voltage than C. But B and D are the same distance from the positive plate. They're going to have the same voltage. That's one way to look at it, kind of a simplified way. Another better way is to think of the work, the work that you would have to do to bring 1 coulomb plus 1 coulomb from B to D. Okay. Well, what does that 1 coulomb want to do? Well, that 1 coulomb wants to race towards the negative plate. So I'm going to have to push on it this way to keep it from racing that way. Okay, remember I got to take it from rest to rest. Now I'm pushing that way, but I'm moving it from B to D that way. So if my force is this way and my displacement, my delta X is that way, what kind of Verk is that? Zero. Zero, okay, zero Verk. On the other hand, if I wanted to take it from A to C, well, again, I have to push it this way to keep it from flying away, but I'm moving it this way. So now my force and my displacement are opposite each other. So from A to C, that's a negative Verk, negative voltage difference. If I'm going from C to A, I'm pushing in the same direction as I'm going. That's positive Verk, positive voltage difference. Does that make sense? Does that speak to you? Okay. Now, we can define a whole line of points, or we could recognize that this picture on this flat screen really represents a three-dimensional situation where we've got a plate coming out into the room, positive on the left and negative on the right. And so in that way of looking at these things, this would be a whole surface of points that all have the same voltage. And we call that an equipotential or equal potential line or surface. Now, I would have called it an equal voltage, again, because I really hate that we call voltage potential sometimes. But this is so prevalent in the literature, in the textbooks, that we have to stick with it. Okay. Now, if I told you that every point on that surface, that dashed line, was 100 volts, and that every point on this surface was 50 volts, and I asked you, what's the voltage on that surface? Tell your neighbor real quick. What is it? What's it got to be?
I guess if you can charge it 75.
The line in the middle, the happiness was out.
What was the naturally?
Seduce what it is happening.
Okay.
Zero would be like.
If you believe the Ed equation, I got the same E field everywhere. And going from this line to that line, the distance is the same as going from this line to that line. So the change in voltage would be the same. So that would be 0 volts. Okay. Now, if I put a test charge up there, would it feel a force or no? Yes or no?
Yes.
Yes or heck yes?
Yes.
Yeah. That voltage is just like elevation. Where I choose my zero of elevation is completely arbitrary and completely unimportant to my physics. Whether I call my zero here on the floor, on the 3rd floor of this building, or whether I call it Main Street Provo, or whether I call it sea level, doesn't change anything, okay? The electric force at that point is going to be exactly the same as it would be anywhere inside those plates, because the electric field is uniform inside those plates. Okay. Let's do a clicker question just to make sure that we get credit for being here today. Which has the higher electric field, point A or point B? I'll get you started here. Okay, now you can click. Those numbers at the top are voltages. Each of those lines is an equipotential line.
The lines are equal. Does it feel small? Yeah. Green and purple. Coming from.
Okay, last call. Get your vote in. Oh, okay. So really, we got 10 of us. The answer is B. Well done. If I think of this as volts per meter, I'm changing my voltage more drastically in 1 meter around point B than I am around point A. And so it's going to be greater at B. And if I were to ask you what direction does the electric field point at B, well, that's just going to be downhill. Okay, it's from high voltage to low voltage. So in this case, it would be that way. And what we find is that these lines, these equipotential lines, have to be perpendicular to the electric field, which gives you the answer to this question: which point will have an equipotential line that passes through the X? Is it A, B, or C? Let me get you started. You can click.
Distance. It's like gonna be like.
I put this slide in here just to show you that the simple equipotential lines and surfaces between plates are not the only equipotential surfaces or lines. We can have more complicated electric fields and still define our equipotential lines. Okay, some of us still need to vote. It's not hard. This is a celebrity Jeopardy question. Can you point to your own head? Okay, last call. Good. B is the correct answer, and E is not the correct answer. Okay. So that line has to be perpendicular to every single field line that it crosses. This has to be 90 degrees. This has to be 90 degrees. Every time it crosses a field line, it has to do it at 90 perpendicular, 90 degrees. Okay. Now, we often encounter something called a dipole. Now, an electric dipole is just a positive charge and a negative charge that have the same size. A hydrogen atom would be an example of an electric dipole. Now, what I've drawn here, the red lines are the electric field lines, okay, that we talked about earlier in this part of the class. The blue lines are equipotential lines, equal potential or equal voltage lines. Now, what you should see when you look at that is a mesa, a tall mesa next to a sinkhole. Tell your neighbor which is the mesa and which is the sinkhole and where the cliff is between them. Okay, which is the mesa and which is the sinkhole?
It's like, I don't.
Right, theoretically, but I get. Lines. Okay, that's field.
That's odd. That's really cool. Now that it's like, the more I think about it. Oh, yeah. What can you start?
Okay,
Flattest.
I hope you all remember that the voltage is higher near a positive charge. And so this would be the mesa, okay? And here's the cliff, and that would be the sinkhole where the voltage is the lowest, okay? Years ago, my wife and I went down southern Utah, and there's a place called Gooseberry Mesa, just right near the southern border of Utah. And if you go up on there, really high up, you can gather, losing my words, petrified wood. It's just all over. And so we were up there with our dogs, picking up pieces of petrified wood for our garden. And next thing we know, this whole group of mountain bikers come racing by really, really fast. There's a really popular place to mountain bike. And then they all of a sudden just swung to a stop and they, Dr. Francis, what are you doing up here? I can't go anywhere. I mean, I can't even go to a restaurant. Too many students. Okay. So in 3 dimensions, if I have a point charge, I would have field lines that go radially out in every direction. We've just shown 3 of those. And indeed, this comes from that textbook that's always wrong, where they put the arrowhead on the end of the line. Sick and wrong, okay? That's not a field line, that's a vector. But the point I want to show you here is that my equipotential surfaces would be nested spheres, kind of like a Russian doll. And the higher voltage sphere would be closer to the positive charge. Okay, I hope you're all seeing that. So in summary, an equipotential surface, no Verc is required to move a charge perpendicular to the field lines because of our definition of Verc. And so that means there is no change in voltage along any surface that's perpendicular to the field lines. And we call those equipotential or same potential surfaces, or I would prefer same voltage surfaces, equivoltage, but it doesn't roll off the tongue. Okay. And the direction of the field lines is from high voltage to low voltage, always, 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 always. Just like gravitational field is from high elevation to low elevation. Check on your neighbor, do a buddy check real quick.
How you doing, buddy? I think it's like, yeah, it's fine.
Okay. We can find that voltage is what we call a state variable, in that it is independent of path. The change in voltage is independent of the path from any point A to any point B. If I go straight across, remember, voltage is how much Verc I would have to do to take 1 coulomb from A to B. Well, the electric field is this way. That plus 1 coulomb wants to fly this way. It's pushed in the direction of the electric field. So I, as an external agent, have to do Verc pushing this way while I move it from A to B. I do positive Verc, a certain amount. Well, what if I went this way? Would I do any Verc? No or heck no? Heck no. And then I got to do Verc there. And then do I do any Verc there? No. then I've got to do Verk there, and then I don't have to do any Verk there. And I think you can see that the Verk I had to do here, plus the Verk I had to do there, is equal to the Verk I had to do there. So whether I go this route or this route, I have the same change in voltage, independent of path. And that means that Bill Cosby's dad was lying when he said he went uphill both ways to school, going and coming. And then later we learned that Bill Cosby himself was lying, and that was a sad day for me because I had. Yes, you have a question about Bill Cosby. Let me just get that. Your question, sir.
I guess I'm still not understanding how there's no work being done to move A upward along the same voltage.
Okay, so from Physics 105, Verk is very different from work that you get paid for, okay? And if I'm pushing in the same direction that something's going, I'm doing positive Verk. If I'm pushing the opposite direction, I'm doing negative Verk. But if I'm pushing perpendicular, zero Verk. And so what that means is that if I put a big heavy load of hay, a bale of hay on my shoulder, and I walk a mile across a level field, I do no work, no physics Verk, because I'm pushing this way and it's moving that way. Well, in the case, if we look at this path here, my delta X, my displacement is up, and my push still has to be that way. I'm pushing to fight the electric field that way, and I'm moving it that way. So I'm doing no Verk. By definition, if you're racing back to what you did on the farm to try to get some intuition on this, no, it's a definition of Verk in physics.
When you move it up, you're pushing right.
Well, I have to push a little bit up to get it started, but once it's started, it just wants to keep going, and then I push a little bit down to get it stopped. But on net, I've got zero. Okay. Good question. Okay. I told you last week that this Van de Graaff generator works because we've got a comb with very sharp teeth. And that comb with very sharp teeth gave us huge electric fields that would throw the electrons off of the point. Well, let's talk about why that is. If I had a piece of metal that was shaped like this, a metal object, because it's metal, the electric field has to be zero everywhere inside that metal. And what that means is that it costs no Verk to move a unit charge on or in a conductor. It's not fighting any field. Now that has ramifications for this week's tutorial homework. I sent you an email pointing out that those homework problems for tutorial 5 are just exactly like the examples in chapter 17, examples 4 and 5. Okay, and that's because we're putting a slab of metal in those homework problems between charged plates. But there's no electric field in the metal. You don't fight anything to move a charge from one place in the metal to the other. And so there's no change in voltage. Now, I also know, you remember, that field lines have to be perpendicular to the surface of a conductor. Okay, the electrons are free to move to their happy place. And if there was an electric field that was tangent to that surface, they'd still be moving. And so the electric field lines have to be perpendicular to the surface. Now you'll notice that where I don't have very much curvature on the metal, my field lines are pretty much almost parallel. But where I've got a sharper point, a greater curvature, they spread out. they spread out, okay? Now, because there's no change in voltage from one point to another point inside that metal, let's say it's 50 volts. Every point in there is 50 volts relative to some reference point. And I'm going to choose the reference point to be right there. Okay, that's what I define to be 0 volts. And when I say that metal is at 50 volts, that means if I were to reach into my pocket, and if I were to pull out +1 coulomb, and if I were to move that 1 coulomb from 0 to anywhere on that metal over there, I would have to do 50 joules of Verc. That's what 50 volts means, is 50 joules for each coulomb. And I got 1. That makes sense? And we just found that it's path independent. If I take that 1 coulomb and move it any way, any path to get to that metal over there, I have to do 50 joules of air. Well, let me talk about 2 paths. One is I take it down here and I come up like this. And I gotta work, 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 I gotta work. Because these field lines are almost parallel, I'm doing the same work pretty much going from here to here as I am from here to here. I gotta work all the way up. That's like the American university system. You got term papers, you've got midterms, you've all semester long, okay? You gotta work. Now, the other path that I can take from 0 is I just come in here towards the sharp point. Well, those field lines are far apart. What does that mean for the electric field? Weak. I don't have much electric field to fight. So this is easy, this is easy, this is easy, this is easy, this is easy. Oh, it's getting hard. It's getting hard, okay? That's like the British university system. There's no homework, there's no term papers, there's no midterms, there's just a final exam that's a killer. And you can just spend the whole semester drinking at the pub, but that last week's gonna make up for it, okay? That last week has to make up for it, okay? Now, what that means is that if I have to do the same amount of Verc, I must be doing a whole lot of Verc when I get close to that point. And that means I'm fighting a huge electric field. Okay. Now, I know that electric field is caused by charge, by surface charge in this case. And so that means I'm going to have a very high concentration of charge near a point and not so much concentration where it's more level. Check on your neighbor. Do a buddy check real quick. Okay.
And I can't.
Are there questions?
It'd be easier.
Yes.
Oh, I see.
Say that again, please.
Is why the positive charge are not evenly distributed along the.
Oh, the positive charge just goes to its happy place. And if this were a perfect sphere, they would be evenly distributed. And that would make the electric field inside the metal 0 by symmetry. But we don't have that symmetry here. And so the key idea here is that if the electric field is going to be 0 in there, the electrons have to, whatever excess charge I have is going to have to put itself in just the right configuration to cancel out. And what we find by that argument I just made is that it congregates near the points. Now, let me, forgot to turn this off, so I used up part of my 5 hours. I've got this pinwheel here. Would you verify that those are sharp? Yeah, okay. Little sharp points on each of these little arms. And I'm going to dump a whole bunch of electrons on this pinwheel. And again, by using this Van de Graaff generator, and what we're going to see, the people in the back aren't going to see it, but those electrons congregate near the points, and the electric field at those points gets so large that it can actually throw the electrons off, and by Newton's third law, that causes the pinwheel to spin. Okay, so there we go. Now, why do we have lightning rods on top of our house? Those lightning rods are very sharp, and the purpose of that lightning rod is not it's not to bring lightning to your house. No one wants to bring lightning to their house. That's just not a smart thing to do. But when there's a lightning storm, the wind and the disturbance that wind is making is creating a large charge separation between the ground and the clouds, okay? And what we do with your sharp lightning rod is we try to get rid of that charge separation by throwing electrons up into the air above your house, so that it neutralizes the path in the air above your house, so the lightning strikes your neighbor and not you, okay? That's the purpose of a lightning rod, is to make it go somewhere else. Now, we have this, this demonstration from the University of Washington, and boy, if I can, there we go. That machine in the back is called a Tobler-Holtz machine, and it works on a principle that we won't understand until later in the semester, but it creates huge voltage differences. Now, this was just a few doors down from my office when I was teaching at the University of Washington many years ago, and it's a beautiful device with gorgeous wood, oak, and the glass is this leaded glass with the picture of a staff with serpents going up, reminiscent of Moses raising up the staff with the serpents. And that's a symbol of dentistry. And this came out of a dental office around 1900. And you got to wonder, what were they using this lightning machine for in a dental office? But we're going to use it in this case to create lightning bolts to hit this house. And he's got a little lever here that he can put up a lightning rod. And I want you to listen carefully for when there's lightning strikes and when there's not. And when there's not lightning strikes, you're going to hear a hissing sound. And that's the electrons being thrown up into the air to neutralize the path. So let's watch this. I'd turn off all the lights if I knew how.
We'll use this model house and a high-voltage electrostatic generator to demonstrate how a lightning rod works. One side of the generator is connected to a metal ball inside the chimney. This sharp rod is also electrically connected to the same side of the generator. The other end of the generator is hooked to this copper sphere, which simulates a charged cloud in the atmosphere. When the generator is cranked with the lightning rod down, large bolts strike the chimney. When the lightning rod is raised, the bolts stop. When the lightning rod is lowered, the large bolts resume.
Now, this next part is not going to be on the exam, but no. In my textbook, not the one you're using, but the one for the physics for poets, we actually put in there that when lightning bolt exchanges the charge, it goes from the ground up, not from the cloud down most of the time. That the path is generated from the top down, but once it's created the charge path, the charge actually moves from ground up. And I put that in the book because a colleague of mine who was an expert on lightning told me it was so, Dick Rubisco, and I trusted him. Well, I didn't really think he was telling me the truth until I saw this video. This is super slow motion. We're setting up the charge path, and once that path reaches the ground, watch what happens. It went from the ground up. My book's right. Okay. Okay. In order to work your homework, we need the idea of capacitance, and it's an easy idea. It's a very simple idea, but we need to cover it, and it's something that you're familiar with. It's essentially how much can it hold? The capacitance of something is how much can it hold? And that begs the question, how much can it hold until what? Until what? Well, if we're talking about a gas tank, the capacity of that gas tank is how much gas it can hold. Well, until what? Well, until it spills out onto your feet. Okay. Now, with conductors, we talk about the capacitance as how much charge it can hold. And then the question begs itself, until what? Until it arcs across the room and kills everybody? We don't want that, okay? And so we have to come up with some measure of until what? And so what we use is how much charge can it hold until we change its voltage relative to some reference point by 1 volt, by 1 volt. How much charge can I shove on this thing before its voltage goes up by 1 volt? Now, there's the operational definition. And I've told you over and over again, that's a capacitance there, C. I've told you when you have a definition that is a ratio, something divided by something else, set the basement equal to 1, and that'll tell you what you're talking about, okay? How much charge do I have to put on something before the voltage difference is 1? Now, suppose I told you that I dumped 6 coulombs of charge on that conductor and its voltage changes by 3 volts. What's the capacitance? Well, I would plug in 6 coulombs, I would plug in 3 volts, and I would get a farad is named after Michael Faraday, a great physicist. And a farad is just, as you can see, a coulomb for each volt. It's just a fancy way of saying a coulomb for each volt, okay? Now, typically, we don't have just one conductor, we have 2. And we charge them up by stealing electrons from one of them and dumping them on the other one. So one of those gets positive and one of those gets negative. And I typically do that with a battery. If I went down and got a standard 1 volt battery, if I could, and I hook that to those conductors, what that's going to do is steal electrons from this conductor, run them through the battery, and dump them on that conductor, so that I would get a voltage difference from A to B of 1 volt or 1 joule for each coulomb. What that means is that I would have to do 1 joule of Verk to get 1 coulomb to go from A to B. And that means I must be fighting a bunch of positive charge here and a bunch of negative charge over here. Yes.
I know you said it's independent path, but if I sent the Coulomb through the wire, through the batteries, still 1 joule.
It is. Yes. And because it costs me nothing to go through a metal wire, all of the fight's going to be in here in the battery. And it's going to be chemical, which we cannot understand because that's in a different building. Okay. Now, even though these are charged up, positive and negative, when I talk about the charge stored in a conductor, I mean a capacitor, I only deal with half of the charge. Okay, I'm always going to have a net charge of 0 because I'm going to have just as much positive charge as I have negative charge. But it's only the electrons that are free to move. Okay, they're the ones that can go through the wires and make my motor go, make my fan turn. They're the things that can do something. And so I only consider the charge on 1 plate. And here's where Ben Franklin got it wrong again. We always take the charge on the positive plate and pretend that it's the positive charges that are going through the wires to get rid of minus signs. And we're going to be doing that a lot in the weeks ahead when we talk about electric circuits. Okay? Now, that capacitance is just Q over delta V. Now, I have here it's called a Wimshurst machine. It does the same thing as a Van de Graaff generator in that it separates electrons from positive charge, and it dumps the electrons in one of these. It's a Leyden jar. A Leyden jar is just a very simple type of capacitor. It's the type that Ben Franklin used, and it's just a non-conductor like a glass jar. That's what he would use as a canning jar. And then he would put a metal foil on the outside of the jar and a metal foil on the inside of the jar. And then one of these would be charged up negative and one would be charged up positive. And the glass is just there to keep it from arcing, to keep it from shorting out, if you will. Okay. Now, I'm going to show you a quick video because our Wimshurst machine here at BYU is broken, and I've looked all over the internet to find a new one, and they just don't make them like they used to. I have here a Wimshurst machine connected to a bank of what are called Leyden jars. Now, Leyden jars are just primitive capacitors, the type that Ben Franklin used. Now, Ben used an old canning jar, a glass jar, and he put a metal foil on the inside and a metal foil on the outside. The glass jar was just to keep the two electrically separated so that the charge couldn't short right from one to the other. Now, what I have here is a set of 4 Leyden jars. In the inside I have aluminum foil, and all of that foil is connected to this structure here, electrically. On the outside I have aluminum foil, and all of that is connected at the bottom to aluminum foil, and that aluminum foil comes right up here to there. Now, the Wimshurst machine you've seen before, it separates charge. It puts negative charge over here, leaving positive charge there when I turn the wheel. We talked about the fact that it takes 30,000 volts to throw a spark through 1 centimeter of dry air. So what I'm doing is I'm storing enough charge to build up the voltage of this thing to 30,000 volts. Now, if I connect these bars electrically to the inside and the outside capacitor bank of that Leyden jar bank, And I'm gonna move that over there. And I'm gonna leave these leads here about 1 centimeter apart again. What I've just done is I've increased the capacitance, the storage ability of this device. I've got a lot more room to store charge. Before what? Before it raises 1 volt. I still have to raise it 30,000 volts to get it to arc across. So tell your neighbor what's going to happen as I turn this crank. I have to store a whole lot more charge before I get up to 30,000 volts. It's going to take forever for me to get up to 30,000 volts. But once I get to 30,000 volts, once I throw that spark, it's all going. Okay? All the charge that I've been storing up is going to, yeah, that's what I mean. That's what I'm talking about. Okay? So I get a much bigger spark. Now, the most common type of capacitor is the parallel plate capacitor, and that we charge up by hooking it to a battery. So we steal electrons from this plate and move them over to that plate. If I move an amount of charge equal to sigma times A, sigma is the surface charge density, times the area of the plates, I set up an electric field. And that electric field depends on how thick the charge is on the plates, the sigma. And that's just a constant. That's on the front page of your exam. Now, if I talk about the voltage between A and B from the negative plate to the positive plate, that's going to be the electric field times the distance between the plates. So I get this formula here. That's the electric field. That's the distance. Now the capacitance is this charge divided by this voltage. And so if I plug those in, you see that the sigma cancels out. It's independent of the charge stored on this device. And what it depends on is just the area of the plates and the distance between the plates and this constant, the permittivity of free space. And that's the simplest form of capacitor. Now, you're never going to have to use that equation in your homework. On every capacitor, typically they come in a shape that looks like a tin can, where you take those plates that are parallel and you wrap them up like toilet paper and put them in the can. You put some sheet in between the two metal plates that's a non-conductor. On the side, you'll have two numbers. One will be the capacitance, how many coulombs I can put on there before it changes by 1 volt. And then you have what's called the breakdown voltage. If you put more than 20 volts on this thing, it's going to break it. It's going to arc across your non-conductor. It's going to shatter the glass between the Leyden jar plates. If I want to know how much charge I can store in that thing, I just multiply both sides of my equation by delta V. What this says is that I can charge 3 coulombs for each 1 volt, and I'm going up to 20 volts. And so 3 coulombs for each volt times 20 volts is going to give me a total of 60 coulombs, which would destroy Provo. But remember, it's 60 positive coulombs on one plate and 60 negative coulombs on the other. So it's actually a total charge of 0. But it's only the electrons that are going to do anything for you. So it's useful. It's useful. Now, I've got here a device. I just want to show you this before you leave. I've got a 0.01 farad capacitor, and I'm going to charge it up. And that light is now blinking, so it's charged up. Now, this really isn't necessary because I can't hear anything anyway, but to set a good example for you, You want to hold your ears. I'm going to discharge this by putting a little metal across the leads. Okay. Was that a big boom? Okay. The point I want to make is that the capacitor is one of the most dangerous things in your lab storeroom. You can charge these things up. Some have a breakdown voltage of 3,000 volts. The one that destroyed my hearing had a breakdown voltage of 3,000 volts. And you could charge that up and put it back on the shelf. And 2 years later, you could go and grab that thing, not knowing that it was fully charged, and pow, you'd be had. So whenever you approach a capacitor, you always put some metal across it, across the terminals, to make sure that it's discharged before you do. Okay, let's stop there and go somewhere else.
Out of his back pocket.